Welcome to today's Explainer. We're going to dive right into a seriously fascinating and honestly kind of terrifying paradigm shift happening in cybersecurity right now. We'll be unpacking some brand new research that exposes a massive structural crack in the very foundation of our digital lives. So let's kick things off by challenging a deeply held assumption. Ask yourself this: if the math behind our digital locks is mathematically perfect, does that actually mean our data is safe? For decades, we've essentially believed that as long as the cryptographic algorithms hold up, our secrets are locked down tight. But what happens when attackers just stop trying to solve the math? What if instead they start looking at exactly how that math is being used in the real world? To figure that out, here's our roadmap for today. We'll start with the cryptographic security illusion, then move into the adaptive AI adversary and exploiting system implementations. After that, we'll look at academic focus versus reality, the quantum acceleration threat, and finally, building cryptographic resilience. All right, part one, the cryptographic security illusion, and why relying on mathematical hardness might actually be a trap. We rely on public key cryptography for, well, pretty much everything, right? From your company's VPNs to massive secure cloud platforms. And we do this under the illusion that our adversaries are computationally bounded. The whole system rests on this computational hardness assumption. Basically, the idea that factoring massive prime numbers is just way too computationally expensive for anyone to actually pull off. We assume algorithms only fail if an adversary tries to brute force them, which, with classical computers, would literally take thousands of years. But, as this research points out, that static assumption is exactly where we are the most vulnerable today. You see, the math isn't failing. Our assumptions are. Moving right along to part two, the adaptive AI adversary, or as I like to call it, the invisible learner. Enter the AI-driven threat, and it starts with something called polymorphic malware. Think of this like an attacker who's constantly changing disguises to slip right past your static defenses. Instead of attacking the cryptography directly, polymorphic malware uses machine learning to actually mutate its observable structure. It evades those static signature-based detections without changing its core malicious function. It's essentially an adversary that learns what your security scanners are looking for, and then intentionally shifts its shape to stay completely unseen, quietly embedding itself near your most sensitive operations. But wait, it gets crazier. Even more dangerous is fully morphing malware. This is a highly advanced, almost biological-like threat that continuously learns and adapts its behavior based on your system's specific defensive reactions. Unlike polymorphic malware, which, just swaps out its disguise, fully morphing malware literally changes its internal execution logic. If your security team deploys a brand new countermeasure, it learns from that friction and evolves its exploitation pathways in real time. It targets the physical conditions under which your cryptography runs, like memory allocation and timing. That makes it incredibly persistent. This perfectly illustrates the AI adversarial optimization loop. The adversary iteratively learns from systemic feedback to refine its attacks, and it does this without ever touching the core math. It observes your system's execution artifacts, uses probabilistic inference to map out your defenses, takes action, and then gauges the environmental response. If a defense blocks it, no problem. It just updates its policy and tries a new, optimized angle. It treats cryptographic compromise not as a brute force math problem, but as a relentless, continuous machine learning optimization process. Okay, part three, exploiting system implementations. This is all about keys, entropy, and trust. These adaptive adversaries are specifically targeting the physical and operational implementation layer. And this is a super vital distinction. The AI isn't breaking RSA or AES encryption, it's attacking the entropy, the literal randomness used to generate the keys in the first place. It uses side channel leakage to measure tiny physical variations in timing, power consumption, or get this, even the acoustic emissions of your server just to infer what the private key is. It intercepts key exchanges and manipulates trust anchors. The math remains absolutely perfect, but the physical implementation leaks the secrets. And that brings us to a crucial point. Once an AI extracts a private key through these side channels, all systemic trust totally collapses. Under classical models, a private key compromise was this rare, exceptional failure. But today, driven by adaptive AI, it's a highly scalable, continuous process. Once a key is compromised, the attacker can generate fraudulent digital signatures that look 100% legitimate. They can intercept and decrypt traffic seamlessly. For all intents and purposes, they become a trusted entity in your system. Let's look at part four,
academic focus versus reality, and this really dangerous research gap. With this massive shift happening in the wild, you might be wondering, well, how is academia addressing this highly adaptive threat? Surprisingly, when researchers analyzed databases of published scientific papers, they found a massive disconnect. Academia is still heavily focused on algorithmic robustness, while the real world is out there battling implementation-level AI attacks. The vast majority of scientific literature on cyber attacks is still obsessed with key length and formal mathematical proofs. There is virtually no significant academic clustering around AI-driven key compromise or fully morphing malware. In stark contrast to that academic focus, a whopping 82% of industry practitioners attribute private key compromises directly to AI-augmented optimization and side-channel inference. When researchers actually sat down with cybersecurity pros in the trenches and looked at real incident response data, they found a completely different reality. The threats that are actually succeeding out there aren't brute force attacks on algorithms. They're adaptive, low-noise exploitations of system implementation. There's just this glaring misalignment between what we're studying in the lab and what's actually taking down our networks. Now for part 5, the quantum acceleration threat. It's basically a ticking clock. Just to heighten the tension a bit more, there's a new computational powerhouse accelerating this already fragile ecosystem. This timeline charts a pretty terrifying trajectory toward quantum-assisted adversaries. These are attackers who can harvest encrypted data today, just hold on to it, and then seamlessly decrypt it tomorrow when quantum algorithms mature. Quantum computing is basically an adversarial accelerator. The real threat isn't just waiting for the 2030s. Attackers are intercepting and storing your encrypted communications right now. It's a harvest now, decrypt later strategy. Now, you might be thinking, hey, upgrading to post-quantum cryptography will save us, right? Well, here is the terrifying reality. Even those systems are exposed. Why? Because they inherit the exact same implementation flaws that AI is already exploiting. Transitioning to new post-quantum algorithms will definitely stop quantum computers from breaking the math, for sure. But post-quantum cryptography still requires entropy, it still uses memory, it still has timing variations, which means it's completely vulnerable to the exact same AI-driven side-channel attacks compromising systems today. A new algorithm simply doesn't fix a leaky implementation. Finally, part 6, building cryptographic resilience and shifting to a dynamic defense paradigm. So if building a mathematically bigger lock won't save us, how do we actively secure our infrastructure against systems that literally learn? We have to fundamentally shift to what's called cryptographic resilience. This is an approach where our defensive monitoring and trust validation learn and adapt just as fast as the adversary. We can no longer treat cryptography as a static install and forget thing. We need AI-aware anomaly detection that flags when a machine learning model is trying to infer our keys. We need continuous entropy validation. We need adaptive key management policies that dynamically rotate and automatically invalidate trust the very second an anomaly is detected. It really all comes down to this core idea. True security is no longer a static mathematical absolute. It has to be a continuous, dynamic equilibrium. The days of relying purely on the size of your cryptographic key are completely over. We are dealing with adversaries that observe, learn, adapt, and optimize in real time. Our defenses must do exactly the same thing. We have to treat trust as something that is provisionally granted and continuously validated. Take a hard look at your own infrastructure today. Are you just relying on the math, or are you actively defending the implementation? The adversary is already learning. The real question is, are you? Thanks for diving into this explainer with me, and I'll catch you next time.